Okay, so I would like to welcome you to ICAPS. I'm delighted to see that this room is now filled. Rob and I, maybe about 10 minutes ago, thought we were going to give a presentation to each other. But it leaves time. So our hosts in Brazil have been really gracious. They put together an incredible event for us. I hope you like the facilities here. And now we're going to kind of engage in the intellectual endeavor. So what I'm going to do is I'm just going to tell you a little bit about the spirit of the conference and how we've tried to shape the tutorial programs, the paper sessions, and then I'll tell you a little bit of the logistics and then try to get away as quickly as possible so that we can go into an exciting set of invited talks. Just so the context is, I think the first time that I went to ICAPS as an invited speaker was in '95. At that time, the field had made dramatic progress in terms of the original kind of ideas, for example, in terms of block stacking, to kind of defining very well what the planning problem is, laying down the beginning of a formal framework, exploring different extensions to that. But we were still planning with about 5 or 6 actions. If you look now, then now we're talking about through incorporating the planning competition through discipline, we're now able to generate plans with about 1,000 actions or more. We're systematically moving from atomic actions to time to continuous and the likes. So the field has made great progress on that. It's also developed its experimental discipline substantially. It's drawn very extensively in pushing search methods, where back in '95 it was really chronological backtracking. So we've made tremendous successes in that direction. The question then ends up being is where do we go for the next decade? And what are the directions to push? Any time that a field really excels at one area, right, then you become strong in that area, and then you need to look for new areas in which to strengthen yourself. So in that spirit, we've been trying to do a number of things in the conference to build upon the strong foundation of the conference, but broaden out a bit. One thing that we've noticed, so for example, last year, there was a set of tutorials on the PR2, and we've seen a bit of a revolution going on in the robotics community, right, through the availability of stable platforms, and then robotic operating systems, and a lower level set of toolboxes so that you don't have to keep replicating, right, your perceptual systems. You don't have to write down another interprocess communication system, and then you can incorporate the higher levels. And there's been an amazing adoption of these kinds of technologies and sharing of technologies within the robotics community, which complement the kind of sharing that we've had within the planning community through the competition and the sharing of the planners. So that presents us a tremendous opportunity. And then the question ends up being is, how do we take the kinds of planning systems that we developed and how do we incorporate them in embodied systems, real-time systems, and other systems that are embedded in the world? So, and then what we're also seeing is that the opportunity for robotics in the real world is becoming substantial. So earlier this week I visited Ambrose and walked through their assembly lines, and I had done this previously with Boeing, and the message that I got at both places were quite impressive. That in the 80s there was an attempt to incorporate robotics within manufacturing. That has been more successful in automotive, but in less structured environments such as the aeronautics industry, robotics didn't really succeed. Now, during the last 4 to 5 years, we've seen a tremendous incorporation of robotics, both within Boeing, Embraer, and other industries. And now they're beginning to shift from saying, how do we have robots that operate alone in safe environments, and then how do we have them start working with human and dealing with more flexible tasks? So I think that's just one of many of the exciting challenges where planning plays a very significant role. So in that perspective, we've had a special track called continuous planning, and then we've carried that theme into our invited talks, our tutorials, and our workshops. So the notion of continuous planning, this term I'm using it as it was kind of originally used in the 90s to mean planning systems that continuously plan, execute, monitor, and adapt to the world. And that is viewed as a multidisciplinary endeavor which draws from many different disciplines. That people now also use the word continual planning to avoid the confusion or the pun with the word continuous planning mean planning within the continuous world. But in this case, we are talking about the more larger context of continuously planning and executing in the real world. And there's a wide range of topics. Planning at real time, planning with mixed, discrete and continuous domains, planning when the world is not directly observable, and the likes. So in order to incorporate that, in just the tutorials and the workshops that you've seen so far, a number of those carry this theme. So for example, there was a tutorial in hybrid systems, estimation, diagnosis, and control that Michael Hoffbauer gave. 2 tutorials on discrete and continuous planning by Scott Sanner, which were both incorporating ideas from model checking and dealing with the mixed discrete and continuous world through the use of symbolic encodings. And then Martin Sackerbacher had planned a tutorial on model-based diagnosis and execution, which is how do you do reasoning with hidden state, although unfortunately that had to be canceled at the last moment. And then there's several workshops that also have this theme of planning execution, which has been a tradition explored within the community. Moving to the technical program, then we've selected 3 invited talks which carry forward this theme, drawing people from very related fields, both within AI, controls, and robotics. So the first talk today that we'll be giving as soon as I get off the stage will be by Rob Ambrose on controlling robots across intermediate time delays. And that gives the perspective from the robotics community, human interaction, and space missions. Tomorrow, George Pappas will be giving a presentation. George comes from the controls robotics community, and there's been a very strong connectivity between the controls community and the formal verification community, first in the context of verifying the trustworthiness of a system, or the conversion, for example, of a system, but now carried into control and planning. So you see a very strong similarity between the use of temporal logic and planning in this community, and then within George's community as well. And then Friday, Tony Cohen will talk to us about building qualitative models for spatial temporal behavior. This comes from the knowledge representation community, who spent a lot of time looking at qualitative temporal and then spatial representations. And more recently, they've been incorporating these qualitative spatial representations, not only in terms of basic inference queries, but also in terms of activity monitoring, one of the essential tasks of continuous planning and execution. And each morning we'll begin with one of those talks. We also had a continuous planning track, which carried a number of the themes that I gave you before. And the philosophy behind this track was to draw people from other disciplines. In order to do that, we incorporated many people from a range of different disciplines into our program committee. So people from the hybrid systems control computation community, robotics, within the AI community, people who do constraint reasoning and reconfigurable systems, right, but real-time aspects. And then a number of related AI communities who are more focused on estimating the state of the world as opposed to generating sets of actions. So the model-based reasoning community, the runtime verification, that's a form of verification community brought online, Bayesian inference and activity recognition. And then a number of the program committee members you'll have also seen, giving invited or giving tutorials. And so there will be one track of papers, or one session of papers this afternoon. From the continuous track. And then also, this year we have the ICAPS competition. That complements the focus of the IPC on faster kind of planning algorithms. It looks at more of the knowledge engineering context as a whole, including elicitation, modeling, model validation and verification, planning, scheduling, and analysis. And we'll hear a report out of that competition later today. So then going to just more generic parts of the program. So if you look at the technical program, then we have 37 full paper presentations. The speakers, remember, you have 20 minutes for a presentation plus 5 minutes of questions. And the session chairs should be very careful to attend to that. We also have a set of short paper presentations which have 15 minutes for the presentation. That results in 13 sessions, mostly in 2 parallel tracks with one track for the 3 best paper prizes, 2 student best paper prizes, and then 1 best paper prize. Now, if you look at the technical sessions, then here's just the list of the different session topics. And you'll notice that the program is really kind of broken into 3 parts. There's 4 tracks which are focused on increasing the performance, right, of our planning systems. As our domains become more and more complex, we have the constant demand for increased performance. There's a range of tracks looking at increasingly expressive planning problems, whether or not we're talking about probabilistic or temporal planning, which we've had a tradition of, as well as planning within a discrete and continuous domain, robot path planning, and incorporating techniques from formal verification such as SMT. And then finally, we have 2 tracks on the application of real-world planning and scheduling and execution within the real world. So that's a very nice, healthy program, and it's nice to see that now we're expanding the level of capability of the planning algorithms. Okay, so then to summarize, so the special events that we'll have are going to be the special track, right, session that you'll see today, the ICAPS results session, and then at the end of the day, we'll have the doctoral consortium posters and the system demonstrations. Tomorrow, we'll have the best papers session and the community meeting, which will include a best thesis dissertation presentation, and then we'll also have the banquet and best reviewer prize, and then we'll also have the Festivus, which for those people who still remember the Seinfeld show will then know what a Festivus is. Otherwise, ask somebody who has a gray beard and find out what the heck it means. Okay, we'll also have an additional special event. There are some people here apparently who like football, and so we will be stopping taking a pause in tomorrow's events for the football game. Okay, so now the logistics. Okay, so in terms of your room, it's fairly easy to navigate around here. 50-50 chances that you're going to be wanting to go to this room, right? For sessions labeled sessions labeled B, and for sessions labeled A, you want to go into Pranya. The plenary events will be in this room. The demos and posters will be in Minas Gerais. The lunches will be in the restaurant, Pedra Bella, and then the banquet will be in a larger room, Brazil. Okay, last thing for information for presenters, please meet your session chair before your session. So in the break beforehand, please talk to them, introduce yourself, and at that time, provide them a copy of your slides, right, PDF or PowerPoint. By giving those, you're giving consent to be able to have your slides posted on the website for the conference. So if you don't want your materials to be presented, then don't provide your material. Please do provide it before you give your presentation, because if you defer till later, then you'll forget to do that, and you'll remember when you get on the plane. Okay, so then finally, so if we just kind of recap the schedule. So the highlights of today will be Rob Ambrose's talk, which we're just about to begin. Then we'll have 3 parallel sessions. We'll have the ICAPS competition results, the DC poster, and the system demos. Tomorrow we have a bit of a shift in the schedule to accommodate for the football game. So note that the best paper session will begin at 1:10. The community meeting has been moved up to 2:40, and then the award meeting is going to be after the football game. And then finally on Friday we'll have Tony Cohen's invited talk. We'll then have 2 parallel sessions and then say farewell early on. Okay, so that's it for the conference. So it's my pleasure to introduce. Are you giving? Oh, is this sound still on? Okay, good. So it's my pleasure to introduce Rob Ambrose. I've known Rob Ambrose probably for at least 15 to 20 years now. Rob is very well known both at NASA and within the robotics community. He received his PhD at University of Texas, and then since then I believe you've been at NASA, kind of moving up the ranks at NASA. Right now he's in charge of he's a division chief at Johnson Space Center in the division that deals with software, robotics, and simulations. He's perhaps best known within the research community for the development of the Robonaut robotic astronaut, right, which is a teleoperated robot in a humanoid form, though there's been a constant effort to increase the level of autonomy for that capability. Robonaut 2 is now on the International Space Station, and Rob has also developed surface versions of Robonaut called Centaur. Rob has also been kind of very actively involved in automation for human space flight, orbital robotics, and the likes. So without further ado, I'll introduce Rob.
Thank you very much and good morning. And thank you, Brian, for inviting me. I'm looking forward to catching a pulse on where planning is and how it might be applied to our work back at NASA. I'm talking today about how to control robots across intermediate time delays, and I'll get into what I think that an intermediate time delay is. But it's a general pursuit that we've had for a number of years, and going back into ancient times, wanting to operate across time and space. Before I start with that, I just want to put a word in for an initiative that I've been working with several other agencies, NSF, NIH, and USDA, something called the National Robotics Initiative. We're in the process of issuing the first rounds of grants from each of the 4 agencies, and we're going to be doing another round next year. This has been a great opportunity for me to work with the other agencies. One of our agreements is that we'll share research results, so it's a great opportunity for us. About a year ago, President Obama announced this initiative at Carnegie Mellon University, and he told some pretty funny robot jokes. As long as they're laughing about robots, we're always happy that they at least mention them. So, controlling across time and space. It's been a long-term pursuit. It's very useful. We think at NASA a lot about great distances of time and space. But in the ancient world, this really was a military problem, and it started in mid-500 BC. King Cyrus was really the first ruler to have such a problem. His empire had grown, it was enormous. And he, I guess, was not wanting to distribute control across his empire. He summered in one part of the empire and he wintered in another part. And so what he did was he built this royal route. And along the route he staged horsemen that could take information up and down the route. And that allowed him to constantly receive feedback across his entire empire, and then issue commands and run the empire, even though it was 2,500 kilometers across. Not long after him, and in conflict with Persia, were the various Greek armies. Maybe they weren't as powerful as the Persian army, and so they had to be a little craftier. So in the way they sent messages, they were a little stealthy about it. They would take a person and shave that person's head and then tattoo on the head a message and then wait for the hair to grow back. So these are messages that are being sent. Later in the talk we'll be talking about millisecond level kind of response. Here they're waiting for a guy's hair to grow back as they send the message. But this was the state of the art in how to do command and control. A few hundred years later, the Romans were conquering again great tracts of land, and as they got to Britain, they were really at the end of their logistical abilities, and so they started building these things called signal towers. They again wanted to be able to command fairly tactically these armies in the field, and so they built these flag towers that were connected by line of sight, and they could issue commands and get feedback on how things were going. One of the key innovations here is they were using text-level symbols, and so they could encode pretty sophisticated messages. But again, they had to bounce the message from flag tower to flag tower across hundreds of miles. Encryption became more sophisticated. In the 1400s, Italian inventor Battista Alberti invented the cipher disk, a pair of concentric wheels with different alphabets that would allow him to encode messages. But again, they were transcribed by hand and then carried by people. By the 19th century, Thomas Jefferson in America was doing the same thing. He had modified the idea to something called the cipher wheel. Many more alphabets involved, harder to crack, but again carried by hand. And these were letters that Thomas Jefferson was writing to his friends, and they were having to be carried by horsemen. And then things really started to take off. By the end of the 19th century, Nikola Tesla had come to the United States and was remote controlling boats. amazing. About the same time Marconi was doing Morse code, in fact, within about a year or so of that, Tesla set up an exhibition at Madison Square Garden and had a boat and would call out to the crowd, what would you like it to do? And someone would say something and he would type and the boat would do it, and it was wireless. And the US Patent Office refused to issue his patents until they came and observed the boat because they thought that it was impossible. This was a major breakthrough, in fact, probably too much of a breakthrough. It was combining too many things all at once. This ability to communicate wirelessly was itself incredible, and the ability of a machine to run on electricity on its own, remarkable. Connecting them together was maybe a step too far. In fact, he went even further. Into the early 20th century, he speculated about the future and was dead on. His first thought was that we will eventually build these things that he called teleautomata, and the tele meant that it was controlled by somebody else. He referred to this as a robot that had borrowed a brain. So it was borrowing the brain from the person who was teleoperating it. But he said that was just the beginning, that eventually these machines would become more sophisticated, and that the most important part of that sophistication would be the equivalence of a human mind, so that the machine would be able to behave as a human does, so that you could anticipate its actions and you could program its actions. He was famous for making some fairly outlandish statements in the press, and here's a couple good quotes. One was talking to a reporter. He said, "You do not see here a wireless torpedo. You see there the first of a race of robots, mechanical men, which will do the laborious work of the human race." Now, this was more than 100 years ago. He spent about a decade trying to convince the admirals in the US Navy to pick up these things that actually were wireless torpedoes, and they didn't buy. At the time, the world was going through the construction of battleships, and proposing something that could take down a battleship was very unpopular. He even brought in Mark Twain, who's Samuel Clemens, as his front man. And even with Mark Twain, he couldn't convince the admirals that they needed to look into this new technology. So by 1907, there's a quote in the New York Times by Tesla saying, "The time is not yet ripe for the teleautomatic art." And he was right. He was 100 years early, maybe not quite. But the admirals were wrong, and just a couple decades later, they were discovering that their giant ships and their battleships were being sunk by very small boats carrying torpedoes. And again, being able to command across time and space was critical to this. In World War II, the German Navy wanted centralized control. So as a submarine would detect an enemy convoy in the Atlantic, they would radio back to the mainland and report the coordinates. And then the mainland would send out signals to all the other submarines, and they would coordinate together and attack all at once on one command, and something that they called Wolfpack tactics. So this was an incredible achievement, to be able to control boats all the way across the ocean to all work together. But it was also the downfall of the tactic. Even though they had an incredible encryption system, by then they had built the Enigma machine to encrypt their commands. The Allied navies started to use direction finders. So they couldn't tell what the message was saying, but they could tell it was coming from over there. And so there must be a sub over there. And that was the downfall of these subs, that even smaller machines called aircraft could fly off and attack the sub as soon as it used its radio. So again, being able to command and control people and machines across great distances is an important capability, not just militarily, but in a lot of domains. A couple decades later, we really got to some pretty sophisticated machines. one of the first unmanned aircraft was built in the 1960s. It was not what I would call a robot. It was not radio controlled because we had learned the lessons of radio being a telltale. It was merely a wind-up toy. It was pre-programmed to fly, but it flew at Mach 3, so that's a pretty good wind-up toy. And it was deployed from the back of an A-12, which was a lot like an SR-71, also going at about Mach 3. So that's a pretty effective machine, and it could fly for thousands of miles. It was unmanned. It would fly a one-way trip, and before crashing, it would eject its data for mechanical recovery. Later in that decade, we were starting to build some of the first unmanned spacecraft. And here we were wanting them to do more than just timed events. There were a number of important timed events like mid-course corrections, but there needed to be some kind of a sensing or some kind of an adaptation that had to be done by the spacecraft, and there was no person there to do it. And it was at a distance where trying to command it from Earth was awkward. In particular, the most important dynamic event was landing, knowing when to turn the engine off and knowing when not to turn the engine off. Landing is a very difficult thing, and if you try and do it in a completely pre-programmed way, it's quite dangerous. So the Surveyor missions were tremendously successful. A few of them failed, but we learned a lot, and this was really the precursor, the robot precursor program for Apollo. It demonstrated mid-course corrections, demonstrated the communication system that would allow us to get data from and send commands to a deep space spacecraft, and then demonstrate that moon landing. It also busted a number of myths about how the moon was made of soft dust, and when landers would land, they would sink up to their antenna. It busted all those myths as well. And then we went to the moon with people. And towards the end of the Apollo program, we sent this amazing machine called the Lunar Rover. It had on board it one of the best early telerobots. It wasn't designed to be driven robotically. You couldn't steer it and control the propulsion from mission control, but you could control the pan tilt unit on the camera. So it was an amazing camera too. It was maybe the precursor to the camera in the back of the room, a small handheld miniature TV station that the astronauts could walk around on the moon with, but also having this camera that could be controlled from Houston with a pan tilt mechanism. They decided to use it as a cameraman. And at the end of the Apollo 15 mission, they parked the rover a safe distance away. And as the ascent module left the surface, they tried to follow it with this camera, and they missed completely. You know, it went, and then the camera looked, and it was too late. So then they tried in Apollo 16 again, and again they missed. So by Apollo 17, and that was looking like it was going to be our last mission, they definitely wanted to film this departure, and so they built a lookup table and a person at mission control using time on a sheet of paper issued commands through the comm system to try and lead the ascent of the ascent module. And there you can go to YouTube and see this clip. It finally worked on the third try. Now, Sheridan, who was doing his graduate work at the time, could have explained to him, you know, that's just not the way to do it. You've got the time constants associated with this pan tilt camera, which are down in sub-seconds. And you're trying to track it with a camera signal that's got 3, 4, 5 seconds of time delay. That's never going to work. So what they ended up doing was just pre-programming it, and they could have pre-programmed it at the robot. And they could have just triggered on an event, and using the clock that it had, it could have swept the pan tilt. They chose to do that with people in the loop. Sheridan was probably busy finishing his PhD and not trying to fix that at the time, but he did some really important work back then. at looking at how time delay affects teleoperator control loops. And by the 90s, that had really solidified a pretty good understanding of what you can and can't do across time delay. And it's important to note that he was really looking at human arms controlling robot arms doing human-like manual dexterity tasks. That was really the focus of the work, and it's probably more general than that. For that class of work, he was saying more than about 50 milliseconds of time delay would prevent you from doing a good job trying to do teleoperator work, especially if you try to do what's called bilateral force feedback, where you're transmitting forces back and forth across the time delay. 50 milliseconds was about the limit that he felt that we should push. But more generally, it's about the time constants of the system. So for example, if the system was a machine to cut a blade of grass, and you would wait till the grass grew to a certain height, and then at that moment you would clip the blade of grass, the time constants in that system are so slow that a 1 hour time delay would probably be okay. That as long as the time delay is much smaller than the time constants, you can have all the command and control go back through the remote site and still do a good job. It just happens that in eye-hand coordination, the time constants are very short, and 50 milliseconds was a good benchmark that Sheridan showed us. So we had, of course, learned this by the time we sent Sojourner to Mars, and we weren't trying to control this machine through time delay, puppeting it like a telerobot. Furthermore, we were going to Mars, where time delays, depending on the way the two planets are aligned, can range from 4 minutes round trip out to 40 minutes. Trying to do a synchronous control with a person in that loop across that kind of time delay doesn't make a lot of sense. So by 96, we recognized that we had to endow the machine with certain abilities on its own to be able to make decisions, to be able to control in a synchronous feedback control system and take care of business, and then we would interact with it in a more asynchronous way. In fact, the way the rover was commanded was with FTP, where the rover would sit and look at a directory, and when a file appeared that had the right name, it would open the file, and if the header in the file had the right words, it would do what followed. And then it would, at the end of the day, FTP back all sorts of great data that it had collected, pictures and other sensor data. Fairly discrete interactions, but effective. And what was key to that was the rover could protect itself. It was not dependent on a person in a synchronous loop looking out for dangers. It could detect those dangers on its own and avoid them. This machine ran for about 3 months. Even with the fairly high-level interaction, it was hard on the people, and there were a lot of lessons learned about how to form up a team to command and interact with a machine like Sojourner, and there was a number of important lessons learned there. Because humans have dynamics too. Back in the 50s, Fitz showed all sorts of problems with putting lags in systems, with people just starting to make mistakes. And that's not just in kind of the eye-hand coordination area either. It's also cognitively. If you issue a command every 5 minutes, that's just long enough to kind of get detached from the context of the system. This would be a good point to inject your favorite attention span joke about kids these days, but it's really true just about humans in general, that trying to engage a system where you're interacting with it in a very discrete and with long intervals is hard on people, and we're not very effective at it. So around 2004, NASA turned its attention back to the moon. The moon has been very patient. It's been approximately where it was in the 60s. waiting for us. I feel like the moon is inevitable. As we build systems to go out into the universe, we only have one moon. If our planet had 2 or 3, I think there would be a lot of debate about where we would go next. But we've only got one. And like a people that are living on the shore of a giant ocean and there's only one island on the horizon, we're curious about that island. And it seems like a good place to start as we would explore the ocean. Similarly, the moon. The moon is about 1.26 seconds speed of light from a normal point to a normal point between the two spheres of the Earth and the moon. So a round trip, if it were perfect, would be about 2.5 seconds. But what we do is we don't run an antenna around the Earth trying to stay directly below that point on the moon, and the explorer on the moon is not directly at that point either. So by the time you bounce signals through geosync satellites and route them between the various NASA centers and get them to the people, you should expect more on the order of about a 10-second round-trip time delay. So you know right away from Sheridan's work, we're not going to be doing fine teleoperator control. But you also could imagine only talking to a robot once a day might feel a little coarse. Talking to the science teams and the robotics teams working on the Mars rovers, I found that there was a desire for more interactivity on the part of the command team. And here was our opportunity. Unlike Mars, which was tens of minutes away, here we would have tens of seconds of delay, and we might have an opportunity to try something new. So we were looking for an intermediate approach. It's not going to be low latency, high bandwidth teleoperation, because the time delay just won't make that possible unless we're doing incredibly boring and slow things on the moon. And it's not going to be sending a message and then waiting to see what happens tomorrow. We want something in the middle. And so our analogies to this are supervision, where a supervisor is interactive with the subordinate, directing but not controlling. By that I mean giving commands in an asynchronous way, but letting the subordinate do what it needs to do a good job. So this is something that we've started to call a supervisory level of autonomy from the robot's point of view, and a supervisory level of control from the human commander's point of view. So in 2004, we looked at what was the best we had in teleoperation, and we had some pretty remarkable abilities. If you have no time delay, you can do some pretty amazing things. So here's a video of the Robonaut 1 system handling one of the hardest things astronauts have ever used in space. This is the torque tool that was developed for repairing the Hubble Space Telescope. Mike Massimino and Nancy Curry had just come back from a shuttle mission, and they had it very fresh in their mind, and they came over and they coached a teleoperator who had never handled these tools. And this was the first try. Mike said, here's what you got to do. You got to hold it with one hand because you don't want to scratch the Hubble, and it's really hard to see, but look for this little hole that rotates around periodically. And Nancy's job inside the shuttle was she would count the hole using a camera and try and keep track of the progress as they were unfastening these fasteners, holding the Hubble's doors closed. Mike also had a bunch of tricks. He showed us that his fat human finger couldn't fit in to get that bolt out because he's wearing this big spacesuit. So he said, use the tool as a way to get that bolt out. Since you've already got the tool on it, just tap it and you can get it out more easily. And then the next step was you have to pull these so-called pip pins, where you have to depress a button and then you can extract it. And they're going through a couple plates. And Mike said the problem was they would get misaligned. You just have to jiggle it. Turns out jiggle it is one of the most important robot functions, and it's pretty good for people too. And he said, the pit pins are tethered so they won't fly off, but keep an eye on it because it'll wrap around your wrist, and you've got to keep an eye on those tethers. So we went through the whole procedure with him, and this was all teleoperated. What I really wanted was a robot with a person, and so we did a number of experiments, again with a teleoperator. And this was from like 2004. I was doing soldering with a tele-robot. So soldering is kind of a four-handed task. I had the robot hold the two wires, and then I would hold the soldering iron and the solder, and the four hands together could solder the wires. And I would just talk to the teleoperator and gesture and point, and the teleoperator would talk to me, and it was just like my buddy Fred was inside the suit. And it worked extremely well. But again, this is teleoperated. So unless you've got really good time delay, you're not going to be able to do that kind of function. So then we started to look at higher levels of autonomy in the Robonaut 1 system. Here again, we were doing a two-agent task where we've got Dr. Bill Bluthman on one end of a strut and Robonaut 1 on the other, and they're trying to maneuver the strut to feed it through a slot. And we tried lots of different ways to do it. We tried voice command, where you would command Robonaut to do what it needed to do. You're not synchronously controlling it now, you're just giving it direction. We tried using arm gestures to point in the direction we would like it to move. And then we used haptic loads where the person on one end of the stick would just push the stick and the robot would sense the forces and kind of go with the flow, responding to the commander. So this was some of our early work beyond teleoperation with the Robonaut system. It really needed some important capabilities like human tracking. This was 8 years ago before the Kinect came out. We thought it was pretty cool, but it wasn't very robust, and I just was confident somebody else was going to be investing in that technology, and I'm glad they did. And we've now been working with the Kinect a lot, working with Xbox. But you see in kind of an inset there, there's a model of what a person might look like, and trying to segment out the person's head and the person's hand and use the distances between them to take the command. Let's just move on. So we had some basic autonomies that were being developed, and so we were thinking about how to do supervision from the remote side, and we built an immersive environment where a person could step into the robot in a kind of a graphical sense and start to operate on objects. And as long as the robot would perceive those objects and had the ability to handle those objects, you could do a lot with that. So the graphical environment was driven by where the robot thought objects were. And it was a pretty effective system that would allow us to handle easily 10 seconds of delay and stay ahead of the robot. It was predicated on some really good autonomies in the machine. So here's one of Rod Gruppen's students. This is Rob Platt, who's now at University of New York, Buffalo, demonstrating what we called the distal reflexive curl, where various objects are detected and the robot would just grab them like an infant grabs an object. When you put your finger in an infant's hand, the infant's fingers curl around it. This meant that it was adapting to the shape of the object, and you didn't have to do that. You could just say grab it, and it would grab it. It also had to be able to identify where those objects were. It had to identify what the object was. Here again, using an early stereo vision system, we could identify tools, and then more importantly, we could estimate their pose in XYZ roll yaw pitch. We also built a data system called the Sensory Egosphere. This was developed by Alan Peters at Vanderbilt and one of his key students, Kim Hambucken, who then came to JSC. The sensory egosphere, according to Peters, acts a lot like the hippocampus in the human brain. That's the lobe of your brain that is surprised when you turn and find the tool you were just using isn't there anymore. That it's keeping track of all the objects and the individuals around you. And that became a very important data structure for us. And we used it to drive our virtual world that we were using to command the machine. So we started to build overlays, and we would have the most recent data coming back from the time delay as a graphical image, and then overlay skeletons of where you would like to command the system. And we started to look at both manipulation and roving. And so these are two of the big dichotomies in robotics: manipulation and roving. Rovers, mobility, tend to be the two main areas. And so we wanted to make sure that what we were thinking about was not too specific to either of those. So throughout the rest of the work, for the last 10 years, we've had a nice mix of both manipulation and mobility systems being commanded. Now take a look. If you're familiar with NASA, you would realize how amazing this slide is. Kim Hambucken built this thing called the Predictive Interactive Graphical Interface, and she integrated it with software from JSC for the simulations, from Ames for some of the 3D visualization, and using the Ensemble software suite from JPL. This is the equivalent of a hat trick to be able to pull this off. It's been a tremendous team combining engineers from all three of those centers, and one of the best intercenter teams I've ever dealt with in my life. That's actually a picture of Kim at the command there. The Piggy system allows these queues of commands to be sent and queued at the robot, and all sorts of insight into the state machine that's running on the robot and where you are in it, so that you can operate on the state machine, edit it, and basically control execution even across time delays. With a focus on the moon, we started doing a number of field tests. Here was one of the first ones in 2006. These field tests were a group called the Desert Rats, and we would go out to rough environments and test our machines. Here's a picture of one of the first tests. That's one of the Robonaut 1s mounted on a Centaur rover, working with a JPL robot called Athlete, which had multiple limbs. Same software being used to command both, even though the machines are very different. Then by 2008, we had started to build a new class of rovers that were scaled for people. So we conducted an experiment comparing two kinds of rovers. If you were going to go to a planetary surface, what kinds of machines should you take with you? Well, we developed two classes. One was called an unpressurized rover, and the other was called a pressurized rover. And the unpressurized rover, we mounted the astronauts on these turrets, hence the name Chariot for the chassis. The astronauts would be in the suits for about 8 hours, and that's pretty tough on the human body. What we found is that putting them in a pressurized cabin and letting them go out only for short intervals was a much better, much more productive approach. They could get in close with good visibility, even sensors that are better than human visibility. They could decide where to park and then get out of the cabin and do a spacewalk. This was a huge breakthrough. As the astronauts were driving in Apollo, it was very hard to operate in a spacesuit. The spacesuits don't bend well. They had a winch that literally crushed the suit down so that they could see over the sill of the suit as they were sitting in a seat. They were bouncing, and we were thinking they weren't doing a lot of observation. They were just trying to survive as they were driving that vehicle. So this was a huge breakthrough, being able to separate suits off quickly and do like a 30-minute EVA was one of the key enabling technologies here. We built this thing called the suit port, where the suits stayed outside and then would separate off. You would climb into them through a pair of hatches, and then you'd close the hatch on the cabin and a hatch on the suit, and then separate. Instead of going for, say, 4 or 8 hours through an airlock, instead of having to depressurize the entire cabin where it would get filthy, instead of bringing the suits back into the cabin covered in dust, this approach allowed the astronauts to get out very quickly and do an effective spacewalk. And here you'll see when they climb back in, they plug their spacesuit in, and from the inside, they climb back into their cabin. Maybe a little sweaty, but not covered in moon dust. So we didn't tell the astronauts, but those rovers they were driving, they're actually robots. They were built to be driven completely robotically, and we spent a lot of time when they weren't watching out in the field driving them from Houston. Even though we were out in Arizona, we were using the same command and control software that we were using for Athlete and the K-10 rovers at Ames. And it's an evolving suite of tools that is coordinated with Piggy. So down in the lower right, you'll see some graphics and interaction that look a lot like the planning software that JPL uses to plan out the next day in a rover's mission. But instead of working it and then FTPing it after you get it right, the robots are running. So you're out ahead of it in execution. You get all sorts of video views back from it. The image there is from the lander looking across the lava field at one of the rovers. But you're driving it, and it's catching up with you. You can stay several steps ahead of it. When it gets to a waypoint and it misses because it had to avoid an obstacle or there was an error in your model, you reset to that point and are able to continue on. It's a very robust way for keeping the robot running and not getting into a pause and wait kind of a mode. We're now testing this, coming back into manipulation. We'd made some progress in mobility, and we have this opportunity now in the manipulation area on space station. We launched the Robonaut 2 system to the space station in 2011 and have had a very successful early part of its life on station. This whole effort really busted a couple myths. We decided to launch the robot in January, and it was January 2010, and it was certified and packed inside the shuttle later that summer, so maybe 7 months. In that 7 months, we took it through testing. All sorts of parts of it failed. We redesigned those parts, took the robot completely apart, reassembled it, recertified it, it passed, and we sent it to the Cape for launch in about 7 or 8 months. So we're busting some myths here that a state-of-the-art robot or any system could never be in space, that it just takes too long. If it's in space, it's probably 10 years old, or 20 years old, or 30 years old. We've definitely busted that myth. Robonaut is arguably one of the most sophisticated robots ever, and it's in space right now. And we also busted the myth that doing things like that's impossible, and that the certification process is so long that you could never hope to do something on a quick notice like this. We busted those myths and hopefully more. Unlike the Robonaut 1 series, the Robonaut 2 is designed from the very beginning as an autonomous machine. It has more computational horsepower in each of the joints of its arm than the entire Robonaut 1 system. It has maybe 300 sensors per upper limb and an amazing distributed control system. It's also a lot faster than the Robonaut 1s and a little bit stronger and a little bit smaller. It, while autonomous, is operated almost exclusively from the ground. We have options. We've just launched on a Russian rocket a teleoperator interface, so we might start doing some teleoperation with Robonaut, but that's really not what the R2s have been about. They've been about autonomy. So here's a clip that shows one of the things that GM and NASA had in common as we came together in the partnership. We want to be safe working around people. So this is a robot that's strong. It can handle 20-pound dumbbells and has much more endurance than humans. What's it going to take for you to be comfortable to be in the same workspace as this machine? Well, we've built a contact safety system that is triply redundant, that has lots of different sensors looking for potential contacts and monitor those contacts and pause the machine. If the contact is beyond a certain threshold in amplitude and frequency, it stops it completely. If it's just a minor contact, it pauses like you just saw in that clip. That's running all the time. These 3 separate layers of software are the key to our safety. Of course, the robot is soft mechanically with series elastic actuation, and it has no real sharps or hard surfaces. It's padded. But the key is to be smart, to be sensate, and to be looking for potential contacts in your world. Because of this, we have now certified this robot to run autonomously when astronauts are in its workspace. So this is typically not done in factories. Typically they put a big cage around a robot, and if you open the cage to go in, it shuts the robot off. GM and NASA both share this vision of robots that are safe enough to be working around you, shoulder to shoulder with humans. So there are a number of key skills that make this possible. Here's one that I find truly remarkable. The student in that earlier work, Rob Platt, came to work with us, and I mentioned he's now a professor himself. He built this haptic learning system. So there's this soft fabric that's got a divot, a protrusion in it, and Rob is using the robot to kind of raster scan the shape of the object using all the incredible force sensors in the fingers of the Robonaut. What he's built here is the equivalent of SLAM, where you look at a scene, you have a map of the scene, and then you, from that, can decide where you must be. He's built a map of the object, and when he touches it with his thumb, he now knows exactly where he is, and he can go and just put his thumb right in the hole, using tactile feedback. And it's very robust. It takes some scanning for the robot in its own sensor space to get to know the object, to build its own model. But then once it makes contact with the object, it's able to quickly figure out where it is. It's like reaching into your pocket and pulling out a coin, or if you have 2 coins, deciding which one it is without using your eyes. An amazing system. I call it tactile SLAM. He has a more sophisticated name for it. Here is more of a space application. We have all these blankets with grommets typically, and he could scan and make contact with the object and then immediately know where he is on the object and move the object to engage it. Again, there's Professor Platt in the background and one of his students training the robot on tactily identifying objects. So again, we're working towards building these machines to serve as our assistants. When you hand an assistant something, they know what it is. What we would like is for the robot to be able to detect the objects with vision, but also haptically, because there are times when they won't be able to look. A modest amount of training. In this case, they were using 3 different soda bottles, and they were subtly different, and enough so that when you hand the robot one, it knows which it is just through haptic interaction. and it just doesn't miss. So with a little bit of training, the machine became a pretty good bottle identifier, and if you were in charge of bottles, this robot would be a really good assistant for you. And one of my favorite tasks for an assistant is to go put tools away. People aren't good at putting tools away, apparently. The robot would be very good at it. You could hand it a tool, it would know what the tool is, it would put it in the right spot, and its memory would be excellent about where it put that tool. And the lower level force control to make contact with the object, and then continue to do that until its sensors perceive the state that is desired, and then it will stop. So this is the task level where we're able to command the machine and say, turn the knob to this setting, and it does it. For manufacturing, we've done this at a very high level now, and I want to make sure I save some time here. This is handling a flexible fabric that's inserted inside the door of a car to keep water out of the cabin when you go through a puddle. They're typically held in a box off to the side that's heated to keep it supple. It's got a bead of glue around it, and as the human feeds it into the door in the assembly line, there are all sorts of complicated tasks. They have to feed a flex cable through a slot in the fabric. In this case, it's doing that using force control and then vision to identify where this flexible cable was to begin with and to verify that it went through the slot. It then puts its finger in those bumps using that haptic feedback, and it pokes those bumps into the metal of the door. Our challenge here was to keep up with the assembly line. This is a very unpopular task for the humans, and the idea was to be able to slip in robots for the stations that caused a lot of wrist injuries for the humans, and let the humans do the other tasks. This one, people would only do this about for less than an hour before they had to move to another station. There were a number of closeout steps and kind of poking it into place. There's that bead of sticky glue around the perimeter, and that was what caused most of the injury. What the job requires is that you have a roller and you roll around the perimeter of that fabric while applying a force. And that's exactly what you don't want to ever do with the human wrist. If you do the same motion while the wrist is under load, you will quickly start to get injuries. The other thing was that people tended to only do it with one hand, and we built a robot that was not just dexterous, it was ambidextrous, and it could do the job with both hands. So you see here, the robot's pulling out these rollers from some holsters that it has, and it's now going to go around the whole perimeter of that fabric, applying a force and doing what they call wetting out the panel. As they roll, it squeezes that glue and gives them a good watertight seal. Very hard on the human wrist, and one of the kinds of tasks that they were most interested in. Here's a task that we've just completed on station. I don't have a video from the station yet. It was just a couple weeks ago. This is the robot on the ground. It was told to configure the power panel in a certain state. And so it has a series of procedures and an understanding of the state of the system and what it needs to do to get the panel into the final outcome state. It has to open and close covers, turn on main power, and then go through a sequence of turning on some other buttons. Often it misses. More often we come over and mess with it just to try and intentionally disrupt it. And it's using vision to identify that it completed the task. And if it comes in to hit a button and the button doesn't light up, it will go back and repeat the task dithering, and trying some other techniques that it has. And only as a last result, call a human operator for help. So in this case, the supervisor on the ground will just say, configure the power system in this state, and the robot can go work with the switches. This will be very important if we ever have to leave the space station for an emergency. All the interfaces on the inside of the space station are built for astronauts to use them, and it would be nice to leave at least one of them behind. So now, this is my last video I'm going to show, kind of bringing back mobility with rovers and manipulations with the Robonaut system. And I'll show you a video that we took with the latest Robonaut 2 system mounted on our latest Centaur rover. This was shot again out in a lava bed in northern Arizona. It's an amazingly capable machine. The rover itself is very articulate. It can go up and down. It can drive sideways or turn on a dime. On one end, it's got a bulldozer blade, and on the other end, it's got a Robonaut. And our thinking was, if the Robonaut can't handle it, the bulldozer takes over. We are commanding it here from Houston across, in this case, a fairly short time delay, probably on the order of like 2 or 3 seconds, designating a rock. It would drive to a standoff position, pose itself, and then grab the rock. Now, because it's a government robot, we immediately would tell it wrong rock, but it didn't mind. It's very patient with its supervisors. We're commanding it with that Piggy system, giving it waypoints, and then it connects the dots. We've got a ever-evolving navigation system that is handling even more challenging obstacles and protecting the system as it does that. There won't be a lot of wind on the moon or on Mars, but you'll see here if there was, you'd really have to keep track of which way the wind is blowing, because that lunar dust is extremely fine. And in fact, at the lava quarry, we found there some of the best lunar simulant in the world because it's created by fracturing the lava to make gravel. Now this was the last test we did. Here we were commanding across a 10-second time delay. The robot positioned itself using mobility, segmented the rock, grasped it, and brought the sample back across 10 seconds. Commanding it again with software developed all across the agency. I think I'll stop there. We had our 2 rovers with people driving it, driving them in the field as well. We drove each rover 200 kilometers. We did a lot of night driving where we drove the rovers, these rovers, after the people left. And that is really the basis for a new approach to going after the moon, where the astronauts land, the rovers are already there, they explore a valley, and then when they leave, the rovers drive robotically, unmanned, to the next valley, or maybe for 6 months, for hundreds of kilometers, very far away, to a new and interesting site. A new set of astronauts land, and then reuse those rovers to explore yet a new part of the moon or Mars. So I have one more. There's another form of mobility that's kind of interesting, and that's called climbing. So this is what's in store for the Robonaut system on station. We've just completed a set of legs, and legs are a much more complicated form of mobility. Unlike astronauts who just fly through the space station, we're going to climb. It's more like rock climbing. It's very deliberate, probably slower than we show in this animation. It's a little creepy. The legs move in a fairly inhuman way, but they can. And they have on their feet grippers that grab the handrails, and actually the grippers are based on the design that the astronauts use for stabilizing themselves. With 2 legs, the arms are free to carry objects, and so that's where our assistant can really take off. It can take tools back to the tool chest. This is actually the design case, trying to get through the hash between different station modules. We selected the length of the legs so that you could reach all the way through. Again, the astronauts just fly through, but we're not going to do that with the robot. Outside things are not quite as tight, and again, we have handrails all over the station for the astronauts to use. I'm not going to show all of this, but again, it's still pretty creepy looking. Probably moving around, reposition itself. Maybe it takes 8 hours to climb from one point to another, and that's fine. There's no urgency with the robot. It's not running on oxygen, and it can get itself into position, set tools up for astronauts, or do routine maintenance. Right now, we're only doing about 1 spacewalk a year on the space station, so having a robot outside that could take care of little things would make a lot of sense. So with that, I'd like to answer any questions you have any time you have remaining. Thank you.
Questions?
Yeah. So you showed the video of the robot putting the car doors together, and it seems like a fairly complicated task. So what I'm wondering is how you teach the robot to do that.
So this is actually one of the most expensive things in robotics, is teaching a new task. The promise of robotics is they can do lots of things, but if every time you try it and teach it something new, you have to start from scratch, it's expensive. So we've started using the robot operating system that Brian mentioned, and it's really reduced our task development time. We've also started some new work in the area of learning. Dr. Steve Hart has recently published some work. Stephen Hart from General Motors, formerly a Rod Rubin grad student, has shown some fairly general behaviors that have allowed us to take some new tasks on and get them working pretty quickly. Where it used to take us maybe a month or 2 months to program a task, we're now down in the order of hours to get a new task going. But a machine like a robot could do so many different jobs that it's very hard to generalize across all tasks. So some tasks we can reprogram in just a couple hours, and we are looking at more general behaviors that learn and allow us to make those transitions to new tasks easier.
Another question? Okay. Arlen?
It was very impressive. So thinking of the challenges that, and of course robotics poses challenges to 10 different communities, focusing on decision-making capabilities of autonomous robots for 10, 20, 30 seconds. What would be an example of a challenge that you face and say, well, we're not there yet?
So my favorite autonomous robot behavior is stop. And especially if people are in the work site, stop is a really good place to start when you're building an autonomous robot. And so many different decisions can lead to stop. So many different situations can make the machine stop. But stop is expensive. It slows everything down. And it's one of the reasons why they want to get rid of those cages in the manufacturing world. So every time you open the door and the assembly line stops, somewhere on the assembly line, there's a car that you don't want to buy because it's been interrupted in its construction. So being able to have enough options that you don't have to just stop, that there are some other workarounds that allow work to continue and while waiting across the time delay for some advice from your supervisor. So thinking of myself, I've got a boss, and if my boss has told me to start working on something, and I get to a point and I need to talk to him or her, rather than stop and do nothing for a week while waiting to work with my boss, I'll have other things to do. And being able to intelligently switch over to some other tasks and keep the system productive, it's where we are right now. And with being able to report back to the supervisor and then let them take a few minutes to think about things. What could the robot do quickly to position itself to keep going when the supervisor says, okay, here's the new plan, so that it's not completely stopped and the robot's still running and it's safe. So I like starting with stop as the base behavior, but being able to default into something more productive that's still safe so that we can get back running more quickly or even switch over to another job, I think is about where we are in the state of the art. So don't forget about stop. It's a very important robot behavior, but let's try and do better than that.
And then one last question.
Computer, which parts were autonomous and which not. So I would like. So I would like to know what's the autonomous capabilities that exactly what kind of task you can do in a fully autonomous way.
So the question was, what was teleoperated, what was autonomous? Everything you saw with the Robonaut 2 was autonomous. Everything. When there was a person in the rover driving, that wasn't even teleoperated, it was being commanded on board. But all the other robot driving was the rover driving was autonomous. Only the early Robonaut 1 videos were teleoperated. Everything, and Tesla's work 100 years ago was teleoperated. Everything else was autonomous.
Doing reasoning about the image as well.
Yes. So in the case of Robonaut 2, there are 5 different imaging systems in the head that are used to identify objects, estimate their pose, look for things like geometry to detect is the switch up or down, and identify state in the system using autonomous perception, which is critical. The subordinate's got to be able to understand the world that it's in and take action, and not ask the person on the other side of the time delay, is the switch up or down? The robot needs to see that, and a rover needs to see that there's an obstacle and avoid it, rather than waiting for somebody to say, that's a rock, be careful. You can't do that across time delay.
Great. Let's thank our speaker. Okay, so we'll see you back promptly at 10:30, and for those people who will be speaking in the next session, then please come up and talk to your session chair before you go off and enjoy yourself. Bye-bye.